Hello, everyone, and welcome to phyloseminar.org. This series of 4 talks will be an introduction to phylogenetics in 4 parts from Master Expositor Paul Lewis. Paul has developed this material of this course for over many years of his teaching at the Woods Hole Molecular Evolution workshop. Today's talk will be about basics of phylogenetic trees and models. If you want to ask a question, and we do encourage questions, you can either tweet at phyloseminar or type your question in the live chat box to the right of the video on YouTube. As I mentioned, today's speaker is Paul Lewis, who is Professor of Ecology and Evolutionary Biology at the University of Connecticut. Paul is a leader in Bayesian phylogenetics theory and practice. Of his many research contributions to phylogenetics, 2 especially stand out to me personally. First, his work on model selection and comparison, leading to several new ways of efficiently calculating marginal likelihoods. And second, his seminal work on non-bifurcating tree inference and its importance in getting accurate phylogenies. Welcome, Paul, and thanks for participating.
Thank you. Can I go ahead and start?
Go for it. You're sounding great.
Okay, sounds good. So this is the first, as Eric said, this is the first of the 4-part series of introductory lectures about phylogenetics. In this first part, I plan to explain some of the jargon surrounding phylogenetic trees, and then explain how to calculate the likelihood of a tree using DNA sequence data. In these lectures, I assume that you've had some algebra and calculus in the past, but I'm trying not to assume that you've remembered very much of it. So trees are graphs that represent phylogenies, and phylogenies represent, I'm paraphrasing here from Encyclopedia Britannica, the evolutionary history of species or more inclusive groups. Because phylogenetic trees are graphs, it makes sense to start by reviewing some terms related to graphs. So graphs have vertices, and which are often called nodes in phylogenetics, and those are connected by edges, which are called branches often in phylogenetics. The vertices attached to just one edge are known as leaf vertices or leaves, but may also be described as terminals or tip nodes. Non-leaf vertices may be called internal nodes. The term topology or tree topology refers to the branching structure of the tree. 2 trees can differ very much in appearance or in the lengths of their edges without differing in their topology. For example, 2 of these 3 trees have the same topology. Can you see the one that differs? Even though tree 2 looks like it's different from the other 2, it nevertheless says, like tree 1, that rice and rose are closest relatives, and that pine is more closely related to both rice and rose than it is to fern. So tree 3 is the odd one out because it makes rice and pine closest relatives. The term taxon, the plural of which is taxa, is used to refer generically to those things represented by the leaf vertices in the tree. Taxa are the entities, for example, species, whose genealogy represents the main goal of a phylogenetic analysis. In this tree, rice, rose, pine, and fern are all separate taxa. A taxon can also be more inclusive, can represent collectively all the descendants of, for example, a given internal node. For example, the group comprising rice, rose, and pine here is one of these higher taxa. In this case, this higher taxon is the sister taxon to fern. So we say that sister taxa are taxa that share an immediate common ancestor. If a group of taxa can be removed from the tree by snipping just one edge, then we say that that group is monophyletic, and often use the term clade when discussing the portion of the tree that we've snipped out. The degree of a vertex or a node in the tree equals the number of edges that are attached to that node. So here's an example of a vertex with degree 1. Here's an example of a vertex with degree 3. And here's an example of a vertex with degree 2. Rooted trees, a tree is said to be rooted if there's a node of degree 2 that represents the most recent common ancestor to all the taxa included in the tree. Unrooted trees have no degree 2 root node, but any unrooted tree can be rooted by inserting a node into any edge. So for example, if we insert a node into this edge here, we can get a rooted tree that looks like this. Is this tree rooted or unrooted? This is kind of a trick question because the answer depends on whether the tree is binary. All the nodes in binary trees have degree 3, with the exception of the root node in the case of a rooted tree, which still has degree 2. In non-binary or multifurcating trees, at least one internal node has degree 4, such as this node, or higher, or it's possible that the root node has degree 3 or higher in a rooted tree. These nodes with advanced degrees are known as polytomies or multiplications. So that's why it's difficult to classify this tree as either rooted or unrooted. It could be a rooted multifurcating tree in which the basal root node has degree 3, or it could be a binary unrooted tree that just happens to be drawn in such a way that it appears to be rooted at a basal polytomy. Sometimes software needs help from you in order to correctly interpret such trees. Trees can have edge lengths that are proportional to the expected number of substitutions per site. If substitution rates vary among lineages, then the distance from an internal node to any of its descendants need not be the same. Such trees are said to have edge lengths that are unconstrained. On the other hand, in ultrametric trees, the distance from the root node to any tip is identical, so all the tips line up nicely on the right in this case. In these diagrams, it's the horizontal portion of the distance that matters. The vertical components are simply there to separate the nodes, and they're not counted when measuring the length of the path between the root and the tip. If edge lengths are proportional to time, then trees are necessarily ultrametric. Hence, ultrametric trees are often called time trees. A split or bipartition is associated with every edge in a tree. If the edge is snipped, for example, this one, the taxa on one side of the break are separated from those on the other side. Here I've used a vertical bar to show that the taxa A, B, and C are on one side of the split and D and E are on the other side. This split separates taxa A and B from C, D, and E on the other side. Splits are often represented by patterns that are created by using two arbitrarily chosen symbols. In this output from a Bayesian phylogenetic analysis, hyphens and asterisks are used to indicate which taxa are on either side of the edge associated with each of these 17 splits. The frequency column contains support values that say something about how confident we can be that a particular split is present in the phylogeny of the group of interest. Trivial splits are splits that are associated with leaves in the tree. They are trivial because they must be present in every tree. Here I've circled the 6 trivial splits associated with the 6 leaves. I've indicated the ordering of taxa below the column of the split patterns down here. This ordering is normally just the order that the taxa appear in the data matrix. A majority rule tree, consensus tree, is a tree that is constructed from all the splits that have a frequency greater than or equal to 50%. And since the total frequency here is 1,000, that would be any split that has a frequency greater than 500. There are only 3 splits in the table here that qualify, and their position in the majority rule tree is shown here. Note that there's maximal support for the split that pinches off D and F, that's this split here, while the support for the split that pinches off A and E is only 74.5%. This means that in some of the sampled trees, taxon A or E actually group with some other taxon. Note that in split 10, which doesn't have a high enough frequency to make it into the consensus tree, A is placed with C. So it places A with C. So this explains some of the remaining 25.5%. Tree files containing parenthetical descriptions of trees, such as the one here shown in red bold text, are produced by most phylogenetic software. These are known as Newick tree descriptions after the Newick Lobster House in Dover, New Hampshire, where the format was invented. You can look at this Wikipedia article for the full story. It's worth spending a few moments showing how these nested sets of parentheses relate to the tree graphs that they describe. We start with the root node and move through the tree in something known as pre-order sequence. So pre-order sequence means, as you'll soon see, that we always visit the left child first, if there is a left child. Then we visit the right sibling, if there is a right sibling, and then we move on from there if there's neither a right sibling or a left child. Whenever we move to the left child of a node, we add a left parenthesis to the Newix string. Whenever a node has a name, we list it immediately after arriving at it, but only if it's a leaf node. If internal nodes have names in the tree, then we only spit out their names the second time we visit them. Here we've written a left parenthesis because we moved to the left child, and we've written an A because that's the name of the taxon associated with this leaf or tip node. Because A is a leaf, it has no left child, so we're forced to go to the right sibling. Whenever we move to a right sibling, we insert a comma into the Newix string. We've also added the name of the right sibling because it is another leaf node. B has neither left child nor right sibling, so we fall back to its immediate ancestor. Whenever we fall back down to an ancestral node, we insert a right parenthesis into the Newix string. The current node has a left child, but we've already explored that part of the tree, so we move on to its right sibling, adding a comma to the Newix string. The move to the left child now results in the insertion of a left parenthesis as well as the name of that leaf. C has no left child but does have a right sibling, so we move there and insert a comma. Moving to the left child now results in its right sib, results in a comma and the name of the leaf node E. E has no left child and no right sib, so we fall back to its ancestral node, adding a right paren to the Newix string. Falling back again adds another right parenthesis. Falling back once more adds the final right parenthesis and leaves us where we started, at the root node. Newix tree descriptions also normally include edge links. The edge links are added to the right of the node name, for example here, and are separated by a colon from the node name. If there is no node name, which is common for internal nodes, such as this one, then the colon plus edge length takes the place of the node name. So let's switch gears now and talk about probabilities. Our ultimate goal today is to understand how to calculate the likelihood of a tree. And likelihoods are probabilities, so we first need to recall some basic facts about probabilities. Probabilities are combined using either the AND rule or the OR rule, or a combination of these two. The AND rule is used whenever you would naturally use the word AND in a statement of the desired probability. For example, the probability of seeing a 1 on one die and a 6 on a second die is 1/6 times 1/6, or 1/36. We used AND because we wanted the joint probability of two separate events, and we get this probability by multiplying the two individual probabilities together. The AND rule comes into play in phylogenetics when we're calculating the probability of the observed data given a tree. In this simple case, we want the probability of starting with an A at the root node and remaining unchanged on branch 1 and remaining unchanged on edge 2 and simultaneously remaining unchanged on edge 3, but changing to a C on edge 4. This statement involves 4 ANDs, and thus the desired probability involves 4 multiplications, which ends up being a product of these 5 terms. You might question why I've presumed to know the states of these ancestral nodes in the tree, but please be patient. We'll fix that with the OR rule in just a minute. If you're tempted to use the word OR in a statement of the desired probability, then you're looking for the probability of one of several mutually exclusive events. For example, what is the probability of seeing either a 1 or a 6 on the roll of a single die? Here we add the two probabilities together to yield 1/3. It is often the case that a combination of the AND and OR rules is necessary. For example, what's the probability of rolling 2 dice and getting a total of 7? There are 6 mutually exclusive combinations that each sum to 7, prompting the OR rule. But each of these combinations in itself involves an application of the AND rule. For example, the leftmost combination here involves seeing a 1 on the top die and a 6 on the bottom die. We can use the OR rule in combination with the AND rule to compute the probability of just the observed states A, and C in this tree. By summing over all possible combinations of ancestral states, we avoid having to assume any particular combination of ancestral states at these nodes. That's good because we don't usually know what these states are at these ancestral nodes. In this case, the probability of each of the 16 possible ancestral state combinations involves the product of these 5 terms, P0, P1, P2, P3, P4. But note, however, that the values of these terms will change depending on which states are present at the ancestral nodes. We'll talk more about that in just a few minutes. If 2 events are independent, we can multiply their individual probabilities to obtain the joint probability. So here the probability of A comma B means the probability that A and B occur at the same time or simultaneously. And this is the probability of A independently, and this is the probability of B independently. For example, if you flip a coin twice and get a head both times, the joint probability is simply the probability of getting the head on the first flip times the probability of getting a head on the second flip. This assumes that the outcome of the second flip does not depend in any way on the outcome of the first flip. Sometimes, however, one event does depend on the outcome of another event. For example, the probability that I walk to work depends to a large extent on the weather. If events are not independent, the conditional probability of one of the events differs depending on the outcome of the other event. We depict such dependencies using the notation shown here for a conditional probability. The conditional probability of the event B, that is, that I walk to work, differs depending on the outcome of the condition, which is A, sunny or rainy. A vertical bar in the notation signifies a conditional probability. The probability statement shown here, in which the joint probability on the left equals a conditional probability times the probability of that condition, is always a true statement. It can be simplified if A and B are independent events, in which case this probability of B given A takes the same value no matter what A is. The probability of the state at the end of an edge in a tree cannot usually be considered independent of the state at the beginning of that edge. A difference over an edge is less probable, all other things being equal, than a similarity across an edge. So the conditional probability of the end state given the beginning state thus changes depending on that beginning state. It's conditional on the beginning state. As another example, the probability of a difference across an edge, here T changes to C, depends on time. So longer times make change more expected, all other things being equal. So it's clear that it would not be possible to see a change like this if no time at all had elapsed. So clearly there's a dependence on time. Now that we've reviewed probabilities, hold on just a second. Oh, so I forgot to talk about conditional independence. Conditional independence means that 2 events are independent of each other, but each is dependent on some third event. For example, these 2 patterns are independent of each other, pattern AGG and TCC, but each is dependent on the tree topology and the edge links in that tree topology. We can thus obtain the joint probability of the 2 patterns by multiplying the individual probabilities of each pattern, but all the probabilities involved are conditional upon the tree. So that's what we mean by conditional independence. Now that we've reviewed probabilities, let's talk about likelihoods. After this first lecture, my hope is that you'll see why likelihood measures the fit of the model to the data. And since trees are a large part of the model, I hope you'll see why the tree having the highest likelihood is considered to be the best estimate of the phylogeny. Suppose I threw down 20 dice onto a table and all of them came up 5. You should be very surprised at this because the odds against this happening, assuming these dice are normal 6-sided dice, is 3.6 quadrillion to 1. So this is assuming that you have a fair dice model in your head. If you change the model in your head to a trick dice model, and now assume that each die has 5 on every side, then suddenly you're no longer surprised at all. The observed outcome is now certain, and you're not surprised at all that you would see every die coming up 5. So there's a relationship between the probability of observed data under a particular model and how surprised you are, or should be, at seeing those data. Under the fair dice model, the probability of seeing that the observed data was extremely small, and you were correspondingly extremely surprised, although probably not as surprised as you should have been. we humans have a notoriously difficult time adequately appreciating very large or very small numbers. Under the trick dice model, the observed data is certain, probability 1, and thus we're not surprised at all. The maximum likelihood criterion says that we should choose the model with the highest likelihood because that model makes us least surprised at the data we've collected. Likelihood serves as a measure of how well the model fits the observed data, so higher likelihood means better fit. If you are a little bit uncomfortable going with the trick dice model here, it is probably because you've never seen such trick dice before in your entire life. So your hesitancy to blindly adopt the model with the highest likelihood, the model that maximum likelihood would recommend, arises from your belief, your hesitancy that arises from your belief that such a model would be very rarely encountered. And this in turn means that you have at least a little bit of Bayesian in your blood. I will try to tease out a little more Bayesian out of you in a later lecture. Why do we even need a term likelihood? Why don't we just use probability for everything? In common parlance, the term likelihood is used interchangeably with the term probability, but there's actually a difference between these terms, the way they're used in statistics. Consider the two possible outcomes of flipping a coin, heads or tails, and consider two different models: a fair coin model, in which is the sort of the normal model in which there's equal probability of coming up heads and tails on any given flip, versus a two heads model that only comes up heads because there are heads on both sides of the coin. Consider this column in which the model is fixed at the fair coin model and all the possible outcomes are considered. This is the situation in which the term probability is normally applied. The model is fixed, the data outcomes vary, and we say that the probability of H given the model is 0.5 and the probability of T given the model is also 0.5. Note that the sum of all the values in this column add to 1, as they should, because we've considered all the possible data outcomes. Contrast this with a row-wise view of this table. Here pretend like we've observed a T after we flip the coin once, and we're instead trying to decide whether the coin is fair or two-sided using these same probabilities. Here we do not expect the numbers in this row to add up to anything in particular. After all, there's no reason we couldn't add a two tails model, which would make the sum different. The model is, in this case, the model is what's variable and the data are fixed. We only have the data that we observed, but we're considering different models for that same data. We say that the likelihood of the fair coin model is 0.5 given the data, and the likelihood of the two heads model given the data is 0 in this case. Note that the likelihood of a model given the data is exactly the same numerical value as the probability of the data given the model. The difference between the terms, the use of these terms, lies in whether you were thinking sort of in a horizontal or vertical way in this kind of table. So we're now ready to calculate the likelihood of the simplest possible tree, namely a single vertex. There's the single vertex, and there's some data associated with that vertex. Suppose you've sequenced 32 nucleotides of the Psi-Eta globin pseudogene from gorilla. We will assume that each site evolves independently, so the likelihood is simply the product of probabilities of each nucleotide in the sequence. By convention, I symbolize these probabilities using the Greek letter pi. So pi A, pi C, pi G, and pi T are known as relative nucleotide frequencies. And since the probability of an A is the same, regardless of where it occurs in the sequence, we can simplify this likelihood expression considerably by just raising each of the 4 nucleotide frequencies to a power equal to the number of sites that have that state. So there are 12 A's in the sequence, so we raise pi A to the power 12. It's the same as just multiplying pi A by itself 12 times. The natural logarithm of a product of numbers equals the sum of the log of each term. So the log likelihood is just the sum of 32 terms. Here I've scrunched it down, the 32 terms down to just 4 terms, each of which is the number of sites having a certain nucleotide state times the log of that nucleotide state's frequency. So this 12 times the log of pi A is, of course, just the same as taking log of pi A and adding it to itself 12 times. So we end up having 32 terms here, even though I've condensed it down to just what looks like 4 terms. The likelihood, when we calculate it using these discrete data, such as sequence data, is a probability, and probabilities always lie between 0 and 1. So here's the likelihood between 0 and 1. This plot of the natural logarithm shows that the log likelihood is necessarily always a negative number. So we use the log likelihoods instead of likelihoods because likelihoods can become so small that computers cannot distinguish them from 0. On a log scale, really tiny numbers, that is numbers close to 0 over here, end up being extremely negative numbers on the log scale. Yet the fact that the log function is monotonically increasing function of the likelihood means that the model with the highest likelihood is guaranteed to also have the highest log likelihood. So we'll always get the same answer regardless of whether we use the likelihood or the log likelihood to measure the model fit. Let's move on now to the next most complicated tree. 2 nodes, here's a node here and a node here, separated by the branch of length v. We'll use the simplest model of DNA substitution, the Jukes-Cantor 1969 model. This model is time reversible, which means that we'll obtain the same likelihood value regardless of where we consider the root of the tree to be. So I'm just going to arbitrarily consider the root of the tree to be at the node on the left. The JC69 model also says that the probability of any given nucleotide considered in isolation is 1/4 or 0.25. We'll talk more about that later. The likelihood calculated using the data for site 1 is the probability of starting with a G at the left or at the root node, that's 1/4, times the conditional probability, this term here, of seeing a G at the right end, given that we started with a G at the left end. So we've had no change in this particular site across the tree, and this is the conditional probability that's associated with no change across the branch. This type of conditional probability is known as a transition probability, and for the case of no difference across the edge equals this 1/4 plus 3/4 e to the minus 4v over 3. We will see shortly how you derive this formula, where this formula comes from. The site likelihood for site 2 is similar. It is 1/4, which is the probability of starting with an A on the left at the root, times the conditional probability of seeing a G at the right end, given that we started with an A on the left end. Note that the transition probability differs depending on whether the starting state equals the ending state. So the starting state and the ending state are not independent events. We have to use the conditional probability in order to calculate that. Also note that the edge length V plays a role in calculating each of these transition probabilities. It appears in both of these. We can easily calculate the likelihood for more data because each site can be classified as either a difference or a similarity. All sites that have different states at the end of the edge can use this formula over here. There are 2 of those shown in red here. And all sites with the same state at both ends of the branch can use the other formula, this one here. There are 30 of those, 32 total sites. I've plotted the log likelihood as a function of V. So V is on the x-axis, log likelihood is on the y-axis. Note how the curve maximizes or peaks out at the value 0.065. So this value is called the maximum likelihood estimate, or MLE, of V. And that value of V makes us least surprised at the data in front of us. The curve drops rapidly off as V gets smaller. So why is that? This quantity V, the branch length, represents the evolutionary distance between these 2 primate taxa. The evolutionary distance, in turn, is measured in terms of the expected number of substitutions per site, which is the rate of substitution multiplied by the time available for substitution. So the branch represents a certain amount of time, and there's a certain rate associated with that branch, and the rate times the time gives you a number, which is the number of substitutions that you would expect for a branch of that, representing that amount of time evolving at that rate. Anytime you multiply a rate by a number, by a time, you get a number. So driving at a rate of 50 miles per hour for 2 hours yields a number, which in this case is the distance traveled, or 100 miles. If you multiply the rate of substitution by the time available for substitution, you get a number. That's the number of substitutions that you would expect. As this branch length V becomes smaller, then it means that either the time is getting shorter or the substitution rate is getting smaller, or both. Under any of these interpretations of V, it becomes increasingly surprising that we would see these 2 differences in these sequences. Any difference in these sequences would be impossible if p were reduced all the way to 0. That's why this curve dives down to minus infinity, because the minus infinity on the log scale corresponds to 0 on the regular scale. Similarly, the data we have observed becomes increasingly surprising as v gets bigger, because at some point you'd expect to see more than 2 differences if either the time or the rate starts increasing without bound. I hope you're beginning to see that the likelihood allows us to fit our model to the data and provides a meaningful way to estimate unknown quantities such as edge lengths. So I want to show you where these transition probabilities come from, at least for the simplest model, the Jukes-Cantor model, which was introduced by Jukes and Cantor in this 1969 book chapter. I'll make use of an imaginary thing that I call an acneon. So this is just a term that I made up. This concept actually is used in phylogenetic theory and theory of stochastic processes. So it's not something that I didn't make up the concept, but I just made up the term that refers to this. Acneons are like substitutions, except that substitutions always result in a different state. So if T were to undergo a substitution, it would have to change to an A, C, or a G. But if it undergoes an acneon, it can change to an A, C, G, or T with equal probability. So it could end up in the same state that it started at. Okay.
Checking my sources. Here's what I found.
So one of the great features of acneons is that their rate mu is directly related to the substitution rate beta. So the rate at which any particular kind of substitution occurs, for example, a substitution might be T to A, the rate at which that occurs is beta, and that's 1/4 of the rate at which acneons occurs. So you have 100 acneons, 25 of those, if you start with T each time, will be A. So if we calculate transition probabilities in terms of these acneons, we can simply substitute beta equals mu over 4 to get the substitution rate, to get that expression in terms of the substitution rate. Turns out that deriving transition probabilities in terms of acneons is much more straightforward than doing the derivation using substitutions. So we'll do it using acneons and switch back to substitutions at the very end. So let's calculate the probability that the end state is G given that the starting state was T. The probability of 0 acneons across a branch that represents a length of time T in an acneon rate of mu is just the Poisson probability of 0 events, where an event in this case is an acneon and the rate of acneons is mu. The probability of at least 1 acneon happening along that branch or that amount of time is just 1 minus the probability of 0 acneons happening. So this is 1 or more, at least 1, just anything except 0. If you think about it, the only acneon that really matters is the last one. As long as the last acneon dropped to G, then it doesn't matter at all what the previous acneons, however many there were, did. So the probability that the end state is G, given the starting state is T, is just the probability that there was at least 1 acneon, that's this term, because without at least 1, we couldn't explain the fact that there was a difference across this edge, times the probability that the last acneon dropped to G, which is the 1/4 here. If we now remember that we can substitute 4 beta in for mu, then we can get the transition probability of the Jukes-Cantor model in terms of substitution rate and time rather than acneons. So we've gotten rid of this make-believe acneon and put in and we now have it in terms of substitutions. The only problem with this is that the transition probabilities that I used before had a v in them rather than this beta times t. If we note that the overall rate of substitution will be 3/4 of the acneon rate, then we can write v equals 3/4 mu t. So whenever there's an acneon, 3 of the 4 possibilities result in a substitution. So the substitution, the expected number of substitutions is 3/4 the expected number of acneons. And when you substitute 4 beta in for mu, the 4's cancel and you get 3 beta t. So we have v equals 3 beta t for this model, which means that we can move the 3 to the other side and equate v over 3 with beta t. So now if we substitute v over 3 in for this beta t, then we have the version of the transition probability formula in terms of branch length that I've been using in my calculations thus far. So if we have a t at one end of a branch, and then we must have at least an a, c, g, or t at the other end of the branch, then the sum of these 4 transition probabilities should be 1.0, because we've accounted for everything that can happen. But it's not. It's actually 1 minus e to the minus 4v over 3. So what have I done wrong here? The transition probability for the case in which the same state appears at both ends of the edge could result possibly from absolutely nothing happening at all. But recall that we assumed that there had been at least one acneon in our transition probability derivation. So we need to add the possibility that there were actually 0 acneons to this particular case in order to account for all the possibilities. So you get a t at both ends of a branch if you have nothing happen at all, or if something happened, but it ended up being a t at the opposite end anyway. So I've been using 1/4 as the probability of the starting state in calculating these site likelihoods. The 1/4 is the relative nucleotide frequency of every state in the Jukes-Cantor model. These quantities are known as equilibrium frequencies, and it's important to understand why, in order to understand why we can use them as the probability of the root state in a tree. Imagine a house with 4 rooms. Each room has 3 doors in which it communicates with all the other rooms. Don't ask me how you get into or out of this house. Now imagine that a bottle of perfume is broken in room C while all the doors are closed. The perfume quickly spreads throughout room C by diffusion. Now if we open all the doors simultaneously, the rate at which perfume molecules are entering rooms A, T, and G from C is in each case beta, and the rate at which perfume molecules are leaving room C is 3 times beta, because there's three doors that are open and perfume molecules are leaving from all 3 of them at a rate beta. So we can say that the molecules are leaving room C at a rate 3 beta, or they're entering room C at a rate minus 3 beta. So if you want to put all these in the same terms, and we can say the rate at which the perfume molecules are entering each of these rooms, this one has to be the negative of the sum of all of those. After some time, the perfume concentration is equal in all rooms because the equilibrium is reached, in which the perfume molecules are diffusing at an equal rate into and out of each room. The plot here shows what happens to room C over time in red on top and in blue on the bottom. In blue on the bottom, it shows what's happened in all the other rooms. So all the rooms reach the same concentration 1/4 at equilibrium, but C starts up here at 1 and drops down to 1/4, whereas all the other rooms start at 0 perfume and rise up to 1/4 to get to the same value. The horizontal axis here represents time. The same thing happens with sequences. So I'm going to try to flip to a little app that illustrates what happens to sequences. The URL for this app is on my slides, which we'll post afterwards, so you can get to this and try it yourself. But what I've got here is a sequence that consists of all A's, and what I'm going to do is move the slider, and that's going to represent time elapsing. And as time elapses, substitutions turn some of those A's to other things, and eventually if you go all the way to the right, you can see the fraction of A dropping there. The fraction of A is going to drop down to about 0.25. So the fraction of A is now about 0.25. So we can think of this curve, this is the transition probability curve, as representing either the fraction of A's left in this poly A sequence that we started with, or if you focus on one particular nucleotide, it's the probability that that nucleotide is in state A after a certain amount of time has elapsed. So in all of our likelihood calculations, we use that latter interpretation of a transition probability, but I find it useful to think about this fractional interpretation, starting with a poly A sequence and seeing how many A's are left after a certain amount of time. I find that interpretation makes it easier to understand how this curve works. So we can also start with basically no no A's in the sequence. We can start with everything except A, C, G's, and T's. And so the fraction of A starts out at 0 at time 0 and grows as substitutions convert those other nucleotides to A's. And then eventually we reach this equilibrium in which there are A's changing to other things and other things changing to A's, and everybody's at basically the same fraction, which is 1/4. The effect of increasing the substitution rate simply makes the approach to equilibrium faster. So now we get to equilibrium by time 2, whereas before we didn't get to equilibrium even up until time 10, or time 10 we're getting close to equilibrium. So basically, this just shows that how, why we consider these equilibrium frequencies what they are. The equilibrium frequencies are what happens if you wait a really long time and this process goes until it reaches equilibrium, kind of like the perfume reaches equilibrium by diffusion over a long period of time. So before I move on to the last part of the talk, I want to talk a little bit more about these equilibrium frequencies. The reason I went through all that is because I wanted to explain why we use equilibrium frequencies as the probability of the states at the root of our tree. So for any particular problem, we can imagine that the evolutionary process has been running for some large amount of time before we get to the root of our particular tree of interest. Even if we were reconstructing the tree of life, it's certainly true that the root of the tree of all extant organisms, the most recent common ancestor of all extant organisms, is still the result of a long period of evolution before that time. And so as a result, we can assume that the process has achieved some sort of equilibrium by the time it gets to the root of our particular tree. So that's why we use these equilibrium frequencies as sort of proxies for the probability of the states at the root of our particular tree. So let's move on to calculating the likelihood for a 4-taxon tree. And this will, once we know how to do it for a 4-taxon tree, we can do it for any larger tree because we'll have covered all of the basic complications involved in calculating likelihoods. So let's take the data for this particular site as an example to use for our calculations. So this is AAGT. So I'm going to put AAGT at the tips of a 4-taxon tree. And then I'm also going to, for the moment, make up some states for these ancestral nodes. This shouldn't bother you that I'm putting in states for these ancestral nodes because you already know that we can integrate over all possible ancestral states to get the probability of just the observed states. But we'll arbitrarily just choose this node here as the root node because we're going to get the same likelihood no matter which place we choose to start. So I'll choose that as the root node, and we'll put in some ancestral states for now, but then we'll integrate those out later. So the likelihood is shown below here for this 4-taxon tree, and it looks ugly, but it's basically almost exactly the same as what we did for the 2-node 1-edge tree, that evolutionary distance calculation that we did. So if you look at this 1/4 times this transition probability, these first 2 terms would be exactly equal to the site likelihood if the tree were just this one branch with 2 sequences at either end. So all we're doing now is adding more terms for all the other branches in the tree. So if we use the equilibrium 1/4 as the probability of seeing the state A at the root, the second and later terms are just the transition probabilities associated with no change over branch 1, no change over branch 2, a change from an A to a G over branch 3, a change from a branch from G to a T over branch 4, and then no change over branch 5. And note that the branch links appear in the transition probabilities associated with each branch. So V5 appears in this transition probability, V4 appears in this one, V3 in this one, and so forth. So if we calculate the likelihood, we have to know the tree topology and the ancestral states and the branch links that are associated with each edge of the tree. So that's to calculate the probability of this constellation here. So what do we do about those ancestral states? Well, we have to do that same calculation for all possible ancestral state combinations. So I call this the brute force approach. It's not particularly the way any program would choose to do this because it's very slow. You can imagine the number of possible combinations grows really fast as the number of taxa increases in trees. So most programs use a method called the pruning algorithm that was advocated by Joe Felsenstein in his famous 1981 paper that represents sort of the foundational paper for all of likelihood-based phylogenetics. So the pruning algorithm works by noticing that many calculations are being done multiple times. For example, these 4 calculations here all involve multiplying the same 2 transition probabilities together. We have the probability that you have a G at the end, given an A at the beginning, times the probability that you have a T at the end of this branch, given an A at the beginning, and that's the same for all 4 of these. And so, basically, we can go through this table and find lots of examples of this where we're doing the same calculation many times, both the rows and the columns. The end result is that even in this small 4-taxon case, we could save a huge amount of computation by just calculating these quantities once and reusing them each time we need them later. This trades off memory, which is needed to store the calculation, the result of the calculation, for time, but we're almost always, assuming we have the memory, we're almost always willing to trade memory for time. So I'm going to end by pointing out that the likelihood of the whole tree is the product of all of these site likelihoods. So we can calculate considerable effort by calculating the likelihood of, say, constant sites having A for every taxon just once and raising this quantity to a power equal to the number of such sites. So if we have exactly the same sites at the same taxa, the pattern is the same, then the likelihood is going to be the same. So we don't need to recalculate that many times. We just need to do it once and then find out how many of these kind of sites there are and raise the likelihood to that particular power. Similarly, the log likelihood is the sum of the logs of the site likelihoods for every site in the data set, because the log of a product is the sum of the logs of the individual components of that. It is this log likelihood that is what is reported by phylogenetic software because, as I mentioned before, the likelihoods, especially if you have a lot of data, are normally numbers that are too small to be represented in a computer. But the log likelihood, even though it's a large negative number and it's a little bit harder to comprehend when you're looking at it, at least it can be stored in a computer and manipulated. So we've discussed only one evolutionary model in this lecture, the JC69 model. In the next lecture, I'm going to survey many of the models in common usage, including codon models and some talk about amino acid models. And I'll discuss important additions to models such as the +I and +G submodels for accommodating among site rate heterogeneity. So that's all I have for part 1, and I'll talk to you again in a month with part 2.
That was really phenomenal. I think that people who maybe aren't familiar with trying to explain phylogenetics don't appreciate all of the amazing metaphors and so on that you use there. So thank you very much for that.
You're welcome.
I'm going to go ahead and just post it. Maybe we'll just pause for a second if anybody has a question or two. And I can just say that I've uploaded those slides to GitHub, and I'll be posting a link to the YouTube page for this.
Okay, thanks.
Yeah, so maybe you can just give us a quick overview of what's happening next time.
The next time I'm going to go through sort of a survey of models. So I'll start with Jukes-Cantor again, and then go through several models that are more complicated than Jukes-Cantor and culminating in the GTR model. And then I'll talk a little bit about amino acid models and how those are very different than the sort of the Jukes-Cantor family or the GTR family. And then we'll talk a little bit about how you assess how good a model is using AIC or likelihood ratio tests or VIC. And then I'll also talk about codon models a little bit. And I'll also try to spend a little time and make use of another one of these D3 applets to try to explain how we can calculate these transition probabilities for these more arbitrary models where we don't necessarily have formulas that we can derive and use like we did for the Jukes-Cantor model for the transition probabilities.
Sounds great. Would it be worth just, I mean, so there's this thing that is sometimes called the pulley principle, and you sort of already defined likelihood in terms of unrooted trees, so maybe that's not necessary, but Would it be
Just the fact that the root can be anywhere in a time reversible
yeah,
model.
just saying a little bit about that right now?
Yeah, so these models are designed to be time reversible. So the probability of starting with state A and going to state B over a certain amount of time is equal in these models to the probability of starting at B and going back to A. And so because of that symmetry, you're going to get, no matter where you start, where you consider the root, you're going to get the same numerical likelihood value. There are models that are not time reversible, but most of the ones we use are time reversible, which is very handy because we can calculate the likelihood in a way that's convenient rather than forcing us to always use a particular starting point. I don't know what else, you can probably speak to this as well as I can, but I'm not sure what else you're sort of looking for.
Yeah, I mean, that's sort of an interesting convenience, and it's also a bit of a limitation of the sorts of models that we use. So for instance, if you have like models that, have the base frequency changes, and I mean,
exactly.
Apparently this is important for deep bacterial and archaeal evolution, that like you might start with one base frequency that's sort of good for one temperature and move to a base frequency that's better for a different temperature or something.
Right. Yeah, I sort of consider that phylogenetics, 102 rather than 101.
Anyway, okay, well, that was a great explanation. I don't see any questions coming up, so I will assume that everybody else found it as clear as I did, and I guess we will see you in about a month.
Okay, sounds good.
Thank you very much.
Thanks, Eric.